chaque fois, la flexibilité, j'ai du bâton de chocolat.
Pas bâti, sous le pas bâti, et elle ne peut pas descendre comme on se passe de moi. Bon, bah c'est sûr, on va.
Sous, elle ne pouvait pas passer.
Ladies and gentlemen, please. Nobel laureates in physics and chemistry, laureates in economic sciences, your excellencies, members of the Academy, ladies and gentlemen. On behalf of the Royal Swedish Academy of Sciences, I wish you all welcome to the 2018 Nobel Lectures in Physics and Chemistry and the lecture of the Swedish Riksbank Prize in Economic Sciences in memory of Alfred Nobel. Alfred Nobel was a truly cosmopolitan and he was multilingual. He was fluent in 6 languages, and the foresight of Alfred Nobel to establish 5 prizes for important achievements with special instructions in his will that they shall not be restricted geographically reflects his international life and mentality. Science is indeed an international endeavor because the natural laws of the universe are universal. We can all learn and benefit from fundamental discoveries made by other humans across the globe. In 2 days from now, we will commemorate Alfred Nobel's exceptional generosity and his wish to make this world a better place. The anniversary of his death, that took place on December 10, 1896, is marked by the Nobel Prize ceremony. The Nobel Prizes have been awarded since 1901. As a biologist, I have to confess that I regret that Alfred Nobel did not devote a prize to the field of biology. But this year, I can nevertheless rejoice over the great impact that the discoveries rewarded in physics and chemistry have had on biology and medicine. All branches of science ultimately abide by the same laws of nature and are more often intimately interwoven with one another than we realize. Given the international generality of the sciences, the political and religious efforts in some regions of our planet to try to restrict the freedom of researchers who strive for the truth and to stifle unwelcome facts about our planet or ourselves is a cause of deep concern to all of us. This would surely have worried Alfred Nobel tremendously. But today, let us instead enjoy the fruits of knowledge, the joy of discovery, ingenuity of inventions and improvements, and the many resulting benefits to humankind. We will hear about the power of light, both to grasp and to cut with exquisite precision, and chemical techniques that use the mechanisms of life to generate knowledge about cells and proteins, leading to production of pharmaceuticals. And we will hear about studies of the complex relationships between resources and economy in our societies, and also incorporating climate. This year we even have an anniversary. This is the 50th time the Swedish Riksbank Prize in Economic Sciences in memory of Alfred Nobel will be awarded. The 2 economy laureates who will speak later today have addressed problems of global magnitude that would undoubtedly have been of greatest interest to Alfred Nobel. So we can look forward to a very interesting and educational and inspiring suite of lectures today. So with that, I now invite my colleague in the Academy of Sciences, Professor Olga Bottner, who is the chairperson of the Nobel Committee of Physics, to introduce the laureates in physics. So once again, welcome everybody to a journey through outstanding achievements.
Over the past 6 decades, lasers and laser-based devices have become indispensable in many areas of society. With its long-range narrow beam that can be focused into a tiny spot, a laser provides high power over a small area. And this is, of course, useful for cutting, drilling, welding, but not only that, it's also useful for laser surgery and laser skin treatment. The laser is truly one of the many examples of how so-called blue sky discovery in fundamental science eventually may transform our daily lives. The Nobel Prize in Physics for 2018 has been awarded for groundbreaking inventions in the field of laser physics to Arthur Ashkin, Gérard Mourou, and Donna Strickland. And all of these three will be giving talks. Unfortunately, Dr. Ashkin will be giving a talk by proxy, but nevertheless sends a greeting. Arthur Ashkin is an American physicist born in September 1922 in Brooklyn, New York. As an undergraduate at Columbia during the Second World War, he worked part-time at the Columbia Radiation Lab, building magnetrons for the US military radar systems. Receiving a BA in 1947, Ashkin moved to Cornell. Here he studied nuclear physics for a doctoral degree, deciding in the end not to pursue a career in this field where his older brother, Julius, already was a renowned scientist participating in the Manhattan Project. Obtaining a PhD in 1952 from Cornell University, Ashkin got an invitation from his former supervisor at Columbia, Sid Millman, to join the Bell Labs and started working there, researching microwaves before switching to lasers. He was the head of the Department of Laser Science at Bell Labs, Holmdel, for over 20 years, from 1963 to 1987, from time to time also filling in as a member of the technical staff. Ashkin's dream was to trap and manipulate atoms. And in 1986, he and his colleague Stephen Chu, Nobel laureate 1997, demonstrated the first stable optical atom trap, later known as optical tweezers. Ashkin then focused on developing the tweezers to capture and study living things, like bacteria, algae, red blood cells, without harming them. His success has a huge impact on biological research, allowing, for instance, to study how infectious organisms attack healthy cells. Although still active, unfortunately, as I said before, Dr. Ashkin cannot be with us today. He sends a greeting, though, and a close associate, Dr. René Jean Essiambre, who will give the talk in his stead. And so I invite Dr. Essiambre to join me on stage.
I'm Art Ashkin. I want to thank the Royal Academy of Sciences for the great honor of a Nobel Prize. And you know I can't be here for when the time comes, but my friend René, who's a fellow Bell Labs man, very good friend, he's going to deliver the lecture in my place. And, well, okay, I hope you enjoy it. Thank you.
So it is a great pleasure to be here today to deliver the 2018 Physics Nobel Prize lecture of Arthur Ashkin. As you just saw in the video, we prepared the presentation together, and it reflects what he wanted to discuss today. So this lecture is on optical tweezers and the application to biological systems. First, I will present a few historical events that shows that our art was interested by the action of light from a very young age. Then I will talk about the early days of optical trapping, light pressure, the origin of laser trapping, optical levitation. And then I will discuss the work that was recognized by the Nobel Committee, optical tweezers, laser trapping of biological particles, and then biological application of optical tweezers. In 1932, Art was 10 years old, and he was fascinated by the Crookes radiometer. So a Crookes radiometer is, it looks like this. It's 4 vanes that are linked together and suspended on the pinwheel. Each of the vanes have a dark side, a black side, and the other side is highly reflective, like act as a mirror. And all of that is within a glass bulb with partial vacuum. So when light shines on a Crookes radiometer, the black side starts to move away from the light, so it starts to move in this clockwise direction here. So the Crookes radiometer is moving due to thermal effects. In 1944, when Art was 22 years old, 22 years old, he was working on the pulse magnetron, like was mentioned earlier. He was at the Columbia Radiation Lab. So he decided one day to shine this magnetron to the diaphragm of a phone earpiece. And the magnetron was operating at 1 kilohertz, and he saw a 1 kilohertz trace on the oscilloscope. At the time, he thought it could be radiation pressure. In 1966, a few years after the laser was invented and demonstrated, Art went to a conference in Phoenix, Arizona, where he saw a video by Rawson. And in the video, you would see the particle inside the laser, in the internal beam of the laser, to start to move in straight line and bounce around. And at the time, the authors, Ranson and May, suggested that it could be a few different things. One was light pressure, the other one was thermal effects. So Art calculated what the light pressure will do and figured out that it could not be light pressure. So after a few months, everybody settled to say that it is thermal effect. But the main impact of this video on Art is to reignite his interest in light pressure. So what is light pressure? So let's consider 2 different types of objects: a metallic mirror that is highly reflective, and a transparent small sphere. So when a photon comes and hits the mirror, if it's a tiny mirror, it's going to start to move in the opposite direction to conserve the momentum as the photon has been reflected and the mirror goes in the other direction. For a power of 1 watt, this corresponds to a force of 10 minus 8 Newton, which may appear extremely small. But let's look at a transparent sphere that is 1 micron in diameter, so it's very small. So if we shine light on it, let's say we have a photon that arrives at the upper part, is deflected downwards, and the sphere will start to move upwards and in reaction to the photon changing its direction so that the momentum is conserved. If the photon arrives in the lower part of the sphere, it's deflected upward and the sphere goes downwards. So this is the basic mechanism for laser trapping. If you have 2 photons going symmetrically located, the small sphere will go forward. For a power of 1 watt on 1 micron sphere, the acceleration it can induce on the sphere is on the order of 100,000 times the force of gravity. So the radiation pressure that appears to be very small on a very small object like a transparent sphere can produce tremendous accelerations. So now let's consider what happened if the sphere is not exactly on the axis of the laser as it was in the previous slide, but now it's half axis. So what will happen to that sphere, the transparent sphere? So the laser has, of course, higher intensity near the center, and the laser goes in that direction, and lower intensity at the edges. So as we saw in the previous animation, if a photon arrives on the upper part of the sphere, it will be deflected, and there will be a force on the sphere. If the photon arrives at the lower part, the force in the other direction on the sphere. So that the sum of the force can be decomposed into two forces: the scattering force, which makes the sphere move in the direction of the beam, a gradient force that makes the sphere go toward the center of the beam. So what is very interesting here is that the sphere will be attracted to the high power region of the laser, which seems a little bit counterintuitive, but it actually happens. So the sphere goes towards the center of the beam. So let's look at a little animation. So the photons are arriving here, more photon at the top because it's near the center, less photon here, and the ball will start to move toward the center of the beam. When it's at the center, it just moves forward to the scattering force, and here it's going to hit a slide, a microscope slide that stops the sphere. So the sphere is trapped by the beam on the left and by the microscope slide on the right. So Art got the idea that, because he saw this phenomenon, that he could actually put two beams counterpropagating and put a sphere in the middle, a transparent sphere, and this sphere will be trapped because the scattering force of this beam and the scattering force of this beam will compensate each other, and the particle will be in equilibrium there. So that's part of his notebook in 1969. And this notebook was signed by Eric Ippen and Peter Wolf, two famous scientists on their own, and signed by Arthur Ashkin on September 8. So here's a little animation on this two-beam trap. So all the photons arrive symmetrically, so the net force on the sphere is 0 and doesn't move. So this is the first all-optical trap. So Art decided in the next year, in 1971, to look at what will happen if he takes the laser and turn it upwards and use gravity as a force to produce a trapping. So here's the laser. So initially, the sphere is sitting on microscope slide. Then we turn on the laser, but it's too low power. The sphere is not levitating. We increase the power, more photons, and the sphere will start to levitate. And eventually, this at a height that is determined by the laser power and the beam divergence. So Art decided that he would try to measure the charge of the electron using an optical levitator. So here's the setup. That was in 1980. So there is a sphere that is levitating, and there is a feedback control where he's monitoring the height of that sphere, and it changes the power of the laser to keep the height the same. So then he shined UV light in the chamber. That created electrons, and he applied difference of voltage, something similar to the Millikan experiment. So the sphere started to acquire charges, and the power of the laser is adjusted automatically to compensate the electric force that the sphere will undergo under this difference of potential. So here are the measurements. So you can see that this is the charging time. So all along the UV light is on, and this is the power of the laser needed to levitate. And you can see as the UV light shines and charges are created on the sphere, the power to levitate changes. And of course, it's actually a step exactly by the power, by the charge of the electron. It's a discrete power change that corresponds to the charge of the electron. And this is a very high accuracy measurement of the electron charge using optical levitators. Now, let's talk about optical tweezers. The term optical tweezers has been coined by Art himself, and he has been rewarded for the Nobel Prize for this work. So, what is optical tweezers? So, a laser here that goes to a high numerical aperture microscope objective, focus the light very tightly, just not too far from the objective. And what happened is that if we look here at a zoom on this location, at the center here, the minimum size of the beam, the waist of the beam, the highest power is in the middle here. Then there is a gradient in the transverse direction that any laser have. It has more power near the center of the beam than on the edges. But now, because of this very tight focusing, there is a gradient of power along the axis of the beam. So now, from the center here to going forward, there is a very big gradient of power. And what is the impact of that? So we have learned from previous slides that a sphere is attracted towards the region of high power. So the sphere will experience a force that's called a gradient force that is not forward, but is backward. So the sphere wants to go back to the center of the laser. And if you have a sufficient focusing, then the gradient force will exceed the scattering force that is always there and produce and attract a small sphere towards the center of the beam, but not exactly at the center. There's a little bit offset where there's a maximum gradient of the light. So the sphere will settle just before the focus. So in a single beam, you can trap a small spherical transparent particle. So let's see it in operation. So here we have an optical levitator, which will be used just to bring the spheres next to the tweezers. On top, you have the optical tweezers. So the sphere is at the bottom of the tank. You turn the laser on. So the tweezer here is a fixed power, a very high intensity near the focus point. Then there is low intensity levitator. It's not sufficient to levitate. Then we increase the power of the levitator. The particle goes up, and then it's trapped. So a particle, let's do it again. So when the particle lifts, it becomes trapped all of a sudden at this location just after the focus. So that's the way an optical tweezers works. So let's now talk about some of the biological application that Art himself measured. So in 1987, Art and Joe Jejitz, his technical assistant, set up a microscope to trap bacteria using 1.06 micron neodymium YAG laser. So he started with non-living organisms and something that doesn't have the shape of a sphere. So here, I'm going to show a video that he took himself, where you can see this irregular particle being moved by an optical tweezer. And you can see, obviously, that it's not circular, but it's going to be manipulated by the optical tweezers. So the laser is at 1 micron, so we cannot see. It's not visible. But when it's turned on, it moves this small object here. So it shows that you don't need a sphere to use optical tweezers to exert force on objects. Then he turns his attention to living organisms. So here's a paramecium, A paramecium is a single-cell organism. It is between 50 and 330 microns, so it's fairly big. It has internal component called organelles, and they range from a few microns to a few tens of microns. Here's a video that Art took where he trapped one of the organelles. So I want to attract your attention here to the white dot, which is an organelle. And he's going to trap the organelle twice. So let's look at the video. So this organelle is trapped, and the paramecium will move. And then when the organelle hits the wall, it's exit the trap, and it's going to be trapped again. And when it hits the wall, it's leave the trap again. And now, let's look at what happens to a tobacco mosaic virus. A tobacco mosaic virus is very long, so it's very different from a sphere. So I want to attract your attention here, this rectangle. So the tobacco mosaic virus is free, it's moving around. Then it's going to be trapped. So now it's trapped, doesn't move. And then it's turned in the inwards. And because it's trapped using by the end of the virus, because the end of the virus refracts light more, and the optical tweezers is stronger. And now, Art decided to trap spermatozoan, and we can listen to him describing what he's doing. This is 1988.
The trap may not, I don't know, the power may not be high enough, or he's too active. Here, let me put up, I'll give you, well, this is about the maximum power.
Let's see it together.
Here, let me see, here, I'm moving him. Now I got a reference to move him, right? Mm-hmm. Here you can see I'm moving him. Mm-hmm. So that's working.
So now let's talk about a few different applications. So molecular motors are biological molecules, molecular machines that are the essential agent of movement in living organisms. So here's an example of the kinesin. The kinesin is a molecular motor that can carry a load. Here, a bead has been attached to a kinesin, and the kinesin is on a microtubule. So the kinesin wants to transport that bead, and that bead is being trapped by an optical tweezer. And this optical tweezer is soft in the sense that it traps the bead, but not too strongly. So the bead is kind of free to move a little bit, and as it moves, it deflects the beam of the tweezer, so it can be detected where the bead is in the tweezer. And if we look now at measurements, those are three different measurements. The step size here, this is a function of time of the position of the bead, and you can see the bead move, and by step size of 8 nanometers. So the bead is kind of, the kinesin is kind of walking along the microtubule. So it's making an 8 nanometer step, stop for a while, another nanometer step, and so on. So now let's look now at something a little bit more advanced, which is the measurement of the DNA on DNA templates. So a DNA template is attached to one bead, which is in a trap. Then the RNA polymerase is attached to another bead, also in a trap. One of the trap is soft, so it lets the bead move. The other one is strong. The bead doesn't move much or at all. And what we're going to observe here is that the NRA polymerase is transcribing the DNA. And we're going to see a video that is at 30 times the speed of the two beads moving from a single DNA and single RNA polymerase in action. So the bead is moving, as you can see. And what brings them together is the RNA polymerase transcription. So now, if we look at the measurements of this distance between the beads, This is a measurement that is about 1200 seconds. So we can zoom on it because it has a very high resolution by a factor of 10. So we see how sometimes there's no motion, sometimes there is motion. And if we zoom even further, we can see that now there are steps of 3.4 Armstrong. So 3.4 Armstrong is only a few atoms wide. And this 3.4 Armstrong corresponds to the distance between the nucleotides of the DNA. There are other applications also of this tweezers. Here are some: biopolymers properties, motion and forces of linear and rotary molecular motors, molecular behaviors of nucleic acid enzymes, folding of structured nucleic acid and proteins, protein binding, and micromanipulation of small objects in general, and probably many more to come. There are also several companies selling optical tweezers for different applications and different types of tweezers. Art also wrote a book in 2006, published in 2006. He wrote it with the help of his assistant of his wife, Aline, where he presents the fundamental of optical trapping. It discusses different biological applications of optical tweezers. It's also an historical account of the development of optical trapping around the world, but also at Bell Lab. So here are some other people closest to him. Joe Jejit, with whom he worked for many decades. His wife of 64 years, Aline, and some of his closest collaborators over the years. Thank you.
Our next speaker is Donna Strickland. Donna is a Canadian experimental physicist born in May 1959 in the city of Guelph in southwestern Ontario. She received her bachelor's degree in engineering physics from McMaster University in Canada in 1981 and obtained a PhD in optics from the University of Rochester, New York in 1989. There, she and her doctoral supervisor, Gérard Mourou, developed a technique to immensely amplify the intensity of short laser pulses without destroying the amplifying medium, which was a severe limitation at the time for the achievable laser peak power. This so-called chirp pulse amplification technique, or CPA for short, was described in a 3 pages long scientific paper published in 1985. Donna was only 26 at the time. And it was Donna Strickland's first scientific publication and a subject of her doctoral thesis. Chirp pulse amplification revolutionized the field of laser science and led to new advances in many different fields, including medicine and the much publicized eye treatments. Donna Strickland is fascinated by lasers. She has worked at the laser division of the Lawrence Livermore National Laboratory and at the Princeton Advanced Technology Center for Photonics and Optoelectronics Materials. In 1997, she joined the physics department of the University of Waterloo, where she is currently a professor leading an ultra-fast laser group that develops high-intensity laser systems for nonlinear optics investigations. She was named a Fellow of the Optical Society of America in 2008 and has chaired several of its committees. In 2013, she served as its president. please join me in welcoming Donna Strickland on stage to tell us about the developments which led to this year's Nobel Prize.
So thank you very much. So I'm here to tell you about how light interacts with matter. And then when the light gets very intense, it changes how it interacts with matter. I'll tell you then how we made an intense laser. And by the time we were finished, we had to rethink how intense light interacted with matter. So to start, we first have to go back and see how does light interact with matter. So through the centuries, scientists wondered, was light made up of particles or was light made up of waves? And it went back and forth. By the end of the 19th century, scientists were pretty firmly in the light is a wave category. So they were doing experiments with different colors of light, shining it on material, and watching electrons come off the material. Now, when they shone the red light, and I'm only going to describe light that we see, the longest wavelength that we see with our eyes is red light, and wavelength is given by the distance between the crests of the wave. When they shone red light on material, electrons did not come off. When they tried to get the light as bright as they could, electrons did not come off. Now, when they switched to green light, which has a little closer spacing of the crests, electrons came off. But they came off with very low speed. They turned up the power of their green light, and more electrons came off, but always with very low speed. And finally, when they tried violet light, which is the shortest wavelength that we can see with our eyes, so the shortest distance between the crests, the electrons came off with higher speeds. And when they turned up the power, more electrons came off, but always with those same speeds. Now, this flies in the face of light being a wave. If you can imagine walking on a beach that's a stony beach, and if you just have small, see, I know I talk so loud I don't need a mic. So when you walk on a beach and there's stones and you just have little ripples in the waves, the stones don't even move. But if the waves are really crashing in, you will see those stones flying up the beach. And this is how waves would usually move objects. And so when we turned up the power of the light, we certainly expected that the electrons would fly off faster, and yet they didn't. So it's this man here, Albert Einstein, who probably thought of almost all of physics all on his own. What he won the Nobel Prize for, though, was explaining this effect. And so we in optics are pretty proud of the fact that this is what he won the Nobel Prize for. So what he figured out was that light actually is quantized in its energy. There is a minimum energy unit of light that we now call the photon. It's a wave-like particle. So what it says, though, is that the total energy in your light is then the energy of an individual photon multiplied by the number of photons. The other thing that he figured out then is that each photon has an energy given by this wavelength. And so I'm going to do an analogy because it's harder for us to feel the energy of light. So we'll use gravity that we all know about standing on the Earth, and that if we dropped a ball from higher up, it would be faster when it hit the ground, the higher up you can drop it. So now a red photon is a small photon. So we're going to imagine playing basketball with a child-size basketball net. And so if it's a red photon playing basketball, no matter how they try, even up on their tippy toes, they cannot reach that net to drop their electron through. And no matter how many of these childlike photons there are, the electron is never going to get through that basketball net. Now, if you have a green light, that's like an adult playing with a child-sized basketball net, and they can actually dunk through. But only barely. They're only standing slightly taller than the basketball net. And so when they drop their ball through, oops, we have to go back. You have to drop your ball. There you go. See, so slow. Because it's just slightly taller. But the violet photon is like your pro basketball player. They're the very tall people. And so they're well above the net. And when they drop their balls through the net, boom, a lot more speed. But it wouldn't matter how many of these violet photons they had. They would all be dropping at the same speed through the net, just more electrons coming off. So usually when people study the photoelectric effect, it's about quantum mechanics. But that's not what I want you to concentrate on. What it really told us about how light interacts with matter is that it's always one photon meeting up with one atom at a time, and they meet with each other. And if that photon has enough energy, more than the energy that the atom is holding onto its electron, it can then send the electron on its way. And when there's more photons coming, they interact with more atoms, but always one photon meeting one atom at a time. And that's how we understood how light interacted with matter through the beginning of the 20th century. And then along came this woman, Maria Gabriel-Meyer, the woman who won the second woman to win a Nobel Prize. Now, I'm not going to talk about her Nobel Prize winning work because I know nothing about it. I'm going to tell you what she did for her PhD in 1930. She published the paper in 1931, and I cited that 1931 paper in my own PhD. So I don't know why she thought about this, right? Maybe she brought her woman's way of looking at science and thought, why don't photons get along? Why don't photons want to work together, right? Because if two photons would just come into that atom at one time, they would share their energy, and two little red photons would have the same energy as one violet photon, and then there we go. It would have an electron come through with pretty high speed. This is what we now call multi-photon ionization, because there's more than one photon in the interaction. She didn't get to call it that. I don't know what she called it. It was all in German. So now we could understand that, but nobody had seen it. Don't forget, Einstein was actually sitting there wondering why the experimentalists were seeing what they were seeing. Maria Gabriel-Meyer, nobody had seen anything like this, so I don't know what made this woman think about it. But in fact, nobody would see this effect for another 30 years. It was Peter Franken's group at the University of Michigan, and I know I have a lot of Michigan people in the audience, that were the first people to see a multi-photon effect. Now, they were doing their experiment not with atoms that would eject electrons, but what happened was that two red photons were momentarily absorbed by an atom, and then when the atom wanted to let that energy go, it didn't let it go as two red photons. It let it go as one photon with twice the energy. So you'll see then that the wavelength here is half. Well, that looks less than half, but whatever. We'll call it a half. Can't have everything right. Anyway, so this is now what we call second harmonic generation, all right? And we now see it more routinely, but this was something to see in 1961. So then it begs the question, why did it take another 30 years to see what Maria Gabriel-Meyer had predicted back in 1931? What was special about 1961? Well, it's already been mentioned in the previous talk. What was special about 1961 is that in 1960, the laser was born. So because I'm giving a Nobel lecture, I do want to honor all of the people that have won Nobel Prizes for the laser. Basov, Prokhorov, and Towns were really honored for developing the maser. The maser came before the laser, and the M is for microwaves rather than light in lasers. Technologically, it was easier to make a maser than a laser, and so that was done in the 50s, and they won a Nobel Prize. But it was the precursor to the laser. Art Shallow then won for laser spectroscopy later on, but he had a lot to do with understanding how a laser works. But I want to give credit to this man, Theodore Maiman, working at Hughes Aircraft. He's the one who won the race. There was a race on at the end of the 50s and into 1960. Who would be the person who would first demonstrate the laser? And it's this man, Ted Maiman. So 1960, the laser was born. And that's why Peter Franken's group could see this nonlinear optical effect. Now, why is that? Regular light, as shining on me very brightly here, sunlight or what have you, is like this bulb right up here. And in normal light, photons of every color is coming off. That's why it looks white. They go off in all directions. And they also don't talk to each other. They all go off whenever the heck they feel like it. No cooperation whatsoever. That's not how a laser works. A laser, as I'm using right here, and I'm going to shine on the wall over there, you will see that the light only goes in the one direction where I shine it. You don't see it going over there because the light's not going into your eyes. The light's going over there. So we already have it concentrated into one beam. You'll also see that the laser is just one color, and in the case of the laser pointer, just green. They also, the photons in the laser, all talk to each other. And when one's at a crest, they're all at a crest. And so each of these photons are going together, and so they are making themselves to be a giant wave. And a giant wave means the density of photons is greater. So let's go back and think about the linear case. Here's what they saw before 1960, just regular light, photons of every color, just in case you don't recognize them, those are the photons waving at you. And because there was no cooperation, the density of the photons is not very high. So also when you maybe take a lens and you think you're putting sunlight down to a point, I'll tell you it's not going to a point. We can only focus light down to a wavelength. So the light that we see is about 1/2 a micron. The laser I built is 1 micron, so we're going to go with that. 1 micron is 1/1000th of a millimeter. And so you can't focus your beam any smaller than that to concentrate your photons any better than that. But the size of an atom is much, much smaller. Now, because I'm standing in Sweden, I'm going to tell you that the dimension of an atom is an angstrom. But we're not really supposed to use that unit anymore. I'm sorry about that, my Swedish friends. We have to say that it's 1/10 of a nanometer, all right? So this atom is actually 10,000 times smaller than you can focus the light. So when you blow up that atom, because of the concentration of photons, you're lucky to have one atom meet one photon. There's really almost no chance of 2 photons finding one atom at the very same time. But not true with a laser light. The laser light have all these single-colored photons happily shaking together. I don't know if mine are shaking together, but they should be shaking together. And so they pack in a lot tighter. And so you have some chance of seeing 2 photons in the volume of the atom at the same time. I want to credit Nicholas Bloomberg, the person who won the Nobel Prize for nonlinear optics. I'm also going to tell you that it took a long time for me to realize there was a difference in multiphoton physics and nonlinear optics, because I was at a conference celebrating 50 years of nonlinear optics. And I'll just tell you that people that study molecules and atoms, those are the atomic physics types, they say when they watch in the atom that they're doing multiphoton physics. Those of us who actually study light coming out, we're doing nonlinear optics. But to me, it was a very subtle difference. So this man won it for nonlinear optics. So here we go. We now have a chance of 2 photons. So this gets me to my PhD. Gerard gave me a paper written by Stephen Harris of Stanford University. And he had this idea that lasers were sort of stuck in the visible to the infrared, but we might want this wonderful type of radiation in high energy photons, past the violet, ultraviolet, maybe even out to the extreme ultraviolet. So for that, we can't just do second harmonic or even third harmonic. He had come up with, theoretically, ways to maybe have 15 photons be grabbed by one atom and release a photon that's got 15 times the energy. So Gerard said, do you want to do that? Just think about this paper and see what you want to do for your PhDs. So I came up with a way to maybe in twice ionized nickel, I would be able to absorb 9 photons. So that was supposed to be my thesis, never got to it. Anyway, that's why I needed a high-intensity laser, and so a laser itself was not going to get 9 photons squeezed into an atom. We needed an intense laser. So how did we do it? So first, I want to go back to this laser that I have in my hand. The power of this laser is about 1 milliwatt, or 1,000th of a watt. I can make it a pulse, 1 second long pulse, by stopping it, opening it up, and shutting it 1 second later. Now, in that pulse of light then, because power is energy per unit time, if my time unit is 1 second, that's 1 millijoule of energy. Now I can also shine that on my hand and it doesn't hurt at all. I won't shine it in your eyes, but I'm going to put it in my hand and tell you that that millijoule hitting my hand every second doesn't hurt at all. And yet my paper, that was only 3 pages long and got me this Nobel Prize, only had 1 millijoule of energy created. It's also all the energy you need to slice your eyeball up. It's all the energy you need to cut glass, and yet it doesn't hurt my hand at all. And so what's the difference? Well, if I had shone that 1 second pulse of light out to where the moon is, and I have no idea where the moon is, but and I couldn't do it anyway, it would be the beginning part of the pulse would actually be, this is always the one that doesn't work for me, let's go. Oh, there we go. The front part of the pulse would actually be 2/3 of the way to the moon before the end of the pulse would leave the laser. That's how fast light travels. And so now in our 1 second pulse, we have 1 millijoule of energy in this 1 second long pulse of light. Now, what did the Franken group have in order to see that very first multiphoton effect? They had light that was 1 millisecond long. So that's 1,000 times shorter, still 300-kilometer long line of light. I will tell you, they had more than a millijoule. They had a joule. So they had 1,000 times shorter and 1,000 times more energy. And then with that millionfold, they were to see the odd time an atom grabbed 2 photons at once. The laser that we built in Rochester, though, was shorter than that. We squeezed it down some more. And in fact, we squeezed it down so that 1 millijoule of energy was in 1 picosecond, or just 1/3 of a millimeter. So all of the many photons that would have stretched 2/3 of the way to the moon were squeezed down till they were just 1/3 of the millimeter. We packed those photons in. So I know that my supervisor and colleague will be coming up here and telling you the amazing things this laser has done for us. I'm sure even some of them are going to be, he's going to talk about things going on in space. But I'm going to bring us back to Earth. I'm going to bring us to Rochester, New York in the United States, where I did my PhD at the Institute of Optics at the University of Rochester. And I did my research here at the Laboratory for Laser Energetics, and there I am back in the day. Now, inside this Laboratory for Laser Energetics was this absolutely beautiful dye laser. It was red and green, and as I've said, it just seemed like a Christmas tree to me, and I wanted to work with Gerard and this wonderful group. It is a dye laser. A dye laser is a type of short pulse laser. In fact, this laser, the pulses were actually 10 times shorter than what I'm talking about, so only 1/30th of a millimeter long. So we had short laser pulses. Problem is, dye lasers don't like to grab their energy and hang on to it, and so you can't get a big energy dye laser. So you can have short pulses, but the reason that the Laboratory for Laser Energetics was there was to study laser fusion. And to study laser fusion, you need a big laser, and they had a big laser. This was known as the Omega laser. It was 24 beams, and it could produce a kilojoule of energy. Not a millijoule, a kilojoule. That's 1,000,000 times more energy. So in the laser lab, we had short pulses and we had big energy lasers, but we couldn't put them together. More than one problem. One, the dye laser had red photons, and this one wants to amplify infrared photons, so they wouldn't have spoken to each other. But there was a bigger problem. When people tried to put slightly short pulses even into these lasers, what they found was that the rod would actually get drilled all the way through, and you were left with a very expensive piece of glass that wasn't any good. So they had to stop trying to put short pulses down their laser rods because these nonlinear optical effects were happening inside the laser rods, and they were drilling holes all the way through them. So that was the conundrum that we were in the early 1980s. And then Gerard had his beautiful idea. So there are no pictures because I hate having my picture taken. I've had to get used to it since October 2nd. But there are no pictures of Gerard and I together. So we were at a meeting a few years back and took this picture. So this is a very simple, beautiful idea. This is what we want here. We want a lot of energy. We want it in a very short pulse. We just don't want that in our amplifier. So if we don't want that in our amplifier, what can we do? Just start with a short pulse, stretch it and make it a long pulse, amplify it up, and then at the end, compress it all the way back down, And here you have what I like to call a laser hammer. So now, how did we actually do it? We're going to go back to this lab, because this was the lab. Now you'll see I've changed the title of it, even though I'm showing you the very same laser. And so the green beam is actually not a green laser. This is the laser back here. It's infrared. You can't see the beam coming out of the laser because it's infrared and we can't see it, neither can the camera. The kind of mirrors that we use in a laser lab direct just the color we want to direct. And so this green light bent at this mirror, but the infrared came on through. It would have gone to a beam dump to protect all of us from feeling the heat of that very strong laser. And so that laser had the same wavelength as the big neodymium glass amplifiers that we wanted to use. So that was the laser I was to use. You can also see there's simply no room in the inn for me. This was one packed lab. But they shoved me into that corner where the infrared came out, and there I am in 1985 with 1.4 kilometers of optical fiber. So why did we need this fiber? Well, there was one advantage of it. It's not why we needed it. Because there was no room for me here, once we had the light going down the fiber, that fiber then went through the air ducts down the length of the Laboratory for Laser Energetics, where I built the amplifier at the other end of the building. That was one thing. But the two other reasons that we needed this fiber is that the laser that pumped the dye laser was not as short as we wanted, and we needed more colors. I'm going to explain why we needed more colors. I don't have time to tell you what nonlinear optical effect made the colors. You'll just have to believe me that it did. And then this is the component, though, what we really needed the fiber for. This was our pulse stretcher. So first, to understand pulse stretching, we have to know, why do we need a lot of colors in order to make a short pulse? If you watch just one of these colors, and we can just do the red one, you see it goes along there, a red wave would go on forever. Now, if you take more colors and you say that you want all of them to start here, you will see then each wavelength starts to come apart. You don't have to go very far until some are peaks while others are troughs. And so if one wave's a peak and the other wave's a trough, they cancel each other out to be nothing. And so the more colors you can add in, the quicker you will get to where it's zero. And so the more colors you have, the shorter pulse you have. So we created the colors in the fiber, and now it's time to stretch it. How does that work? Well, in the way that light interacts with matter, I said that the red photons have the least energy. When they meet up with their atoms, they sort of shake hands, but then they say, we have, have nothing in common, off you go. So they actually run faster than the green, and by the time it's a blue photon, they're actually considering some time, do we or do we not want to interchange our energy? And it takes a little longer for that blue one to decide no and keep on going. So now if you go down fiber, you will see that the red ran, the green walked, and the blue sort of crawled. And if you go down something like 1.4 kilometers of fiber, well, the red ran, the green, and now you have a long pulse. So I want to explain the name of chirped pulse amplification. A bird's chirp is called a chirp because the sound frequency changes in time through the note that he's making. So you'll see that the way to get a long pulse is to have the red frequencies out first, and then the green, and then the blue. So through our laser pulse now, the frequency changes, and that's called a chirp. It's called chirp pulse amplification because this is now our stretched pulse that we want to amplify up. So how does the amplification work? So it's some material that has some atoms and sitting there, not doing anything. They have to be excited by some kind of energy source. The original lasers and the laser that I used used flash lamps. You'll see that it lights up most, not all, most of the atoms. And a good storage medium will hang on to that energy and stay excited until a photon decides to come by. So then you can have a photon come along, boop, and meet up with an atom. And because we've excited these atoms so they have the very same energy as the photon that we're going to try to amplify, they meet each other, and the photon says to the atom, I'll take your energy with me. And now we have two photons, and that atom lost its energy. Those two photons are marching in step together, and they meet two more atoms, and now we have four photons, and we've given up 2 atoms of energy, and by the end, we'll have 8 photons, and they've given up the 4 more atoms of energy. Now, this is actually very wasteful because you'll see that by the end of it, we've left most of the energy there in the amplifier. So that's a complete waste, and we don't want to do that. If it was a laser, we would put mirrors on either end and have it go back and forth until we steal all of that energy. And this is then why we have to keep building huge lasers if we want a lot of energy. The laser rod itself determines the energy per unit area that you can take. And if you want to grab it all, you actually have to put in almost that much energy to start to snowplow through and take the energy. So each amplification gets a certain energy per unit area. If you want more energy, you must make your beam bigger, you must make your amplifier bigger, and you plow through again. The other thing I want to point out then is that the laser material decides what's the energy per unit area, but the nonlinear things that can cause damage is the energy per unit volume. So once you know what laser you're using, that determines how much you must stretch the pulse so that you keep it below any kind of damage threshold. So that's why we would have to chirp based on the type of laser that we used. So now that we're amplified up, it's just time to compress. And so with a pair of parallel gratings, gratings act like prisms that send different colors of light out to different angles. And so if you watch the path, and you'll see the red, because it was stretched, is further ahead than the green, and the blue is trailing, that when it comes off this grating and each goes in their own angles, that by the time the blue one has managed to get to the grating, the red one had to travel all the way back here and could get here, so that when they all leave the second grating, they're all going together, and we've put all of the photons back together in time, and so we have a short pulse. So then it was just time to measure it. My colleague Steve Williamson came into my lab with his street camera one night, and together we measured, did I or did I not actually have an intense short pulse, and the answer was yes. So we were very happy that night in 1985. So what did we do with it? Well, remember, I wanted to study harmonic generation. That proved too difficult. So we're going to go back to the idea of multiphoton ionization. And we thought that we would just kick that electron and give it so much energy that it would be able to come out of this well that it sits in the atom. And so all those photons would come up and kick that electron out. That's what we were expecting to see, but that's not what we saw. We had made such an intense laser that the photons were packed in there so tight, we no longer had to worry about them being photons. It was back to being just one giant wave. Now, although it's a short pulse wave, so each crest gets a little bit more intense and a little bit more intense. And so what happens when you have a giant wave is that it interacts with the atom that was sitting in its potential. My head can be the electron. And the wave would push it this way, and then the wave would push it that way, and then it pushed it more, and it pushed it more. And finally, it pushed it so much that electron was allowed to go out of the well. But not only does it go out of the well, it goes out of the well into this giant electric force. And it is like a cannon being shot right out of there. Now, it can either leave, or in 2 femtoseconds, that light's towing back, and it may be driven right back to the ionic core. It just depends. And I'm not here to tell you about what happens. Oops, let me show you. Did I show you at least the electron going out? No, there we go. The electron at least went out. I'm going to leave that to my PhD supervisor, colleague and friend Gerard Maru, to tell you about what we understand now about the new understanding intense laser light interacting with atoms. And I will just thank all the people. I want to thank the people that built the original CPA with me, of course, Gerard, but also Steve Williamson and Marcel Bouvier, who are here with me today. Gerard likes to tell people how I said that CPA would not be a good PhD project, or thesis, could not be my PhD thesis. I don't know why he tells the story, because I was right. It could not be. I had to do science with it, which I did multiphoton ionization, and I want to thank the gentleman that helped me with that project as well. And finally, I would like to thank the creative team at the University of Waterloo for making these wonderful slides for me. Thank you very much.
Our next speaker is Professor Gérard Mourou, who's a French scientist and a pioneer in the field of laser physics. He was born in June 1944 in Albertville in the French Alps, a town probably best known for hosting the 1992 Winter Olympics, at least until now. Mourou started his career in physics at the University of Grenoble-Alpes, getting his diploma in 1967 and moving on to first Quebec and then Paris to work on his doctoral thesis. He received his doctorate from Pierre and Marie Curie University in Paris in 1973. Gérard Mourou spent a large part of his career in the United States, in particular at the Laboratory for Laser Energetics at the University of Rochester, New York, where one of his doctoral students, as we just heard, was Donna Strickland. Together, the pair devised the chirp pulse amplification technique, which today is at the core of most high-powered laser facilities in the world. In 1988, Mourou joined the University of Michigan in Ann Arbor, where he founded the Center for Ultra-Fast Optical Science. He returned to France in 2005 and became the director of the Laboratory of Applied Optics at the campus of École Polytechnique in Palaiseau, a post which he held until 2008. Mourou is a visionary, aiming to create lasers with unprecedented power. He initiated the multi-petawatt Apollon laser project in France and coordinates the large European extreme light infrastructure, ELI, that will host even more powerful lasers in Romania, Hungary, and the Czech Republic. He's currently also the field director of ICEST, the International Center for Zeta and Exawatt Science and Technology, established in France in 2011 to, among other things, develop the field of laser-based particle physics. Gérard Mourou has been the recipient of many prestigious prizes, but I dare say that this year's Nobel Prize must be the icing on the cake. With that, I'd like to invite Professor Mourou to join me on stage to give a talk staking out the future of high-intensity lasers. Professor Mourou.
Well, thank you very much for coming, friends, colleagues, former students, and so on. Well, it's always a dangerous act, to act up behind Donna, Anyway, I'm going to try, Donna. It's also a pleasure because there is many of my students in the audience. Students or co-worker, and for me it's very refreshing. It's like when we had our group meetings, at Rochester, or at Michigan, and so on. Anyway, so I'm going to tell you. Can we blow this picture a little bit bigger? Yes. Okay, so I'm going really to talk about my passion about extreme light. So Donna gave you all the background, how to build these high-intensity lasers and so on. You don't need much more than that, okay? And but I'm going to tell you what you can do with that, okay? Because it's true that it's only recently that we had this phenomenal intensity available, and so there is many new discovery which are being made. Okay, so that's my passion for light. Okay, and do I have? Why does it work? Okay, I can maybe act. Okay, I can act here. So everything, like Donna said, everything and started with Ted Naiman, in 1960. I'm sorry, again. Yes. And there's one thing, which really strikes me about light is a variety of things we can do, okay? And as Art Ashkin, showed that what you can do, first thing is maybe you can slow down atoms. And it's a very, very interesting phenomenon we have seen with the tweezers and so on. And this, it doesn't work, it's okay. People, used it intensively, were very successfully, and trying to really use the light to decelerate atoms. And that led to the field of quantum optics and cold atoms. And you have Steve Chu in the first row here, which got the Nobel Prize with co-antanology, and also Bill Phillips. And so that led this fact that we can really slow down the atoms to very, very small times velocity. Very important. It's another way to say that it's a way also to make it atoms very cold and reach temperatures, which are, I think, the coldest temperature we can produce now. Okay, now the other thing you can do, and this is what is exciting, okay? You can do just the opposite. You can accelerate particles. And you can accelerate particles like electrons, for instance, to the speed of light, or very close to the speed of light, okay? And this led really to a new field, which we call relativistic optics. I will tell you why we call relativistic optics in a minute. We know that light is relativistic, of course, per definition, almost. And so that, the fact that we can now accelerate particles to the speed of light then led, of course, now to an enormous field, which deals with accelerator physics, nuclear physics, cosmology, nonlinear QED, general relativity, extra-dimension physics, you name it. Very large physics. Okay, so I don't have to go to talk about CPA. We heard Donna saying it, of course, because we are going to need CPA, of course, to accelerate this particle and so on. So so CPA, we stretch the pulse, we amplify, we compress it, and finally, in order to get very short pulses. I'd like to say one thing, because it was a completely novel concept at the time, and because everybody, as you've seen, was into dye lasers, okay? Especially the guys at Bell Lab at that time. And here we came with Donna with solid-state lasers. And so it didn't grab the attention of many people, except, I will say, a couple of one. One, for instance, was Suni Swanberg, who just visited my lab, because he had a hint that was something special. And also, I had the visit of people from Lawrence Livermore Laboratory, Mike Campbell, and so on. Mike is in the audience because, like me, they understood immediately that it was something important for power, increasing the power of lasers. Okay, so now with this CPA technique, what is fascinating is you can really produce very, very high peak power, and we are going to use this high power. I will show you in a minute. But just to give you a sense, the peak power, okay, of the light is in a now it's in a petawatt range, okay, which is about 1,000 times the total power of the worldwide grid, the global grid, okay? But of course, for femtoseconds, 10 minus 15 seconds. But nevertheless, it's extremely important. And if you take now this power, this petawatt power, and you focus it, like Donna said, over on a spot size, which is a wavelength of light. You cannot really go less than that, so typically a micrometers or so. Then you get a fabulous amount of energy density on a very small spot. And this, of course, is leading to absolutely new application. Just to give you an idea, okay, light, like the first speaker showed, and Art Ashkin and was fascinated by, really deliver pressures. But when you are talking about pressure light at a petawatt level, when you focus that on a small spot size, you can really produce pressures which correspond to about 10 million Eiffel Tower on the top of your finger. So it is the largest pressure that you can produce on Earth is with light, with photons. This is amazing. So now this is really the evolutions of intensity as a function of years, okay? From the 1960, where Mayman invented the laser, and the first first 10 years, new technique improved the power and Q switching, mod locking, and then the intensity plateaued. It plateaued because, like Donna said, you are damaging. If you go higher, you are damaging your laser inside. You damage. You're putting this nice big track, in your solid state amplifier, and of course makes your advisor very unhappy, right, Donna? And she learned the hard way. So anyway, in order to prevent Donna making mistake, I said, well, that's not the way to do it. Let's do it this way. Okay, let's invent the CPA, okay? So she wouldn't really damage rod anymore. Okay, so we did, she built it, and the CPA, and then we could really now, we are not limited by the breakdowns of material, and we could really climb up now the intensities. And now, since the 85, when we did it, the intensity, I have to say, has increased enormously, okay? 8 or 9 orders of magnitude, okay? And it's going to go further up, okay? With lasers like Apollon that is being built, lasers which is part of the ELI infrastructures, Hungary and Romania and Prague and so on. So it's going up. And as we are going up, of course, we are traversing new regimes of physics. So the first one, and Donna said it, we started to really observe multiphoton ionization differently and so on, and observe what she was saying. And so we climbed up this as we climb up the intensity, then we go into relativistic optics. Why relativistic optics? Because for the first times, when you can see something, this means that you have electrons which are agitated, and because they are agitated, they are really producing light, which are coming and striking your eyes. Okay, so, but in a case of when you are passing 10 to the 18 watt per square centimeter or so, then what happens is now the electrons in your atoms move by a large amount and move at the speed of light. So the electrons, not the light, but the electrons are really moving at the speed of light. So that's a very interesting regime, you know, which leads to a lot of effect and so on. So now, of course, if you are pushing, this is what we are trying to do now. If you are pushing the intensity up, you know, like we are trying to do with Apollon, Eli, and so on, then you go into the ultra-relativistic regime, and this time it is because not only the electrons can be moved at the speed of light, but also the protons which are massive, they are 2,000 times the mass of the electrons, so they are more massive, but at 10 to the 25 or so watt per square centimeter, they move at the speed of light, and that's going to be very important. Then finally, if we push even the intensity even higher, and I won't say exactly how we're going to do that. Jonathan Wheeler in the audience, and we can talk about it. But so we go into this regime where light interact with vacuum. Okay, like my friend Pissinchen says, we are boiling the vacuum. Okay, we are really separating the particles, real particles, and virtual particle in vacuum, and this is what we can do. And at this regime, which is 10 to the 28, 10 to the 29 watt per square centimeters. Okay, and basically what we do is we materialize the vacuum. Okay. Anyway, so moving right along. Okay, again. So now there's one thing. If we go back to the regimes, you know, at 10 to the 14 and so on, you know, then we can really use these femtosecond lasers. So we don't add, for instance, to micro machines, to remove, to ablate material very, very precisely. The reason is femtosecond lasers are so good for that is because if you are using, for example, a continuous laser and you're shining the continuous laser on a target, then you are going finally to hit the whole volumes of a target, so you cannot really micro machine with that. Now, if you are using pulses which are much shorter nanosecond pulses, which is for us is infinity, you know, it's very long, but you do better because, of course, the heat doesn't have the time to propagate before the block is molten, and then you have the femtosecond laser where you come with a very, very short pulse and you deposit the energy, and the temperature, I mean the heat, doesn't have the time to propagate, and you make these very nice holes. And it's a very, very precise way to really ablate the materials. And this gives you some idea, you know, of what we could do, what we can do. In fact, very easily now it's really widely done everywhere. And you can see that we can really make holes and so on very precisely. There is no collateral damage, you know, it's very clean. And very small. Okay, you see that we have feature size which is less than the micrometers, you know, in size, and no damages. So of course now one beautiful way to use this laser is to do eye surgery, because after all, eyes, is some biological tissue, and also is not the kind of things where you have to be accurate with eyes. And so we thought about that. In fact, we thought, because we had this little mishap happening in my lab, and this is one of my students who is in the audience, got a line in the laser, got a laser in his eyes. And immediately, we took the student, to the hospital, and they met ophthalmologist who is also here, Ron Kurtz, and so Ron Kurtz looked at Ditardu eyes, both are here, and he said, "Wow, this is very strange." And yes, he got hit by the laser, but it's strange. And so Ditardu, he said, what is strange? Well, it's strange because the damage on your retina is perfect. So that immediately, of course, we had the University of Michigan, excited about it. They put some money in it, and then that started the field of femtosecond laser, which is a very, very important field. Okay, so this is just to give you an idea what we can do, on the cornea. We can use it for all kind of things, we can in ophthalmology, and so it was very exciting. In fact, so if you are, I'm just show here, if you have a 50 picosecond laser, which is long for us, okay, or if you have 300 femtosecond, you can really create this flap, very, very nicely, and this is being done, now. There's also few ophthalmologists here in the audience, and it's great. So now I had a movie showing this creation of a flap, but I have to say that, and after some comments, people say, well, if you show this movie, maybe some people are not going to stand it, for it, because it's. So I'm not going to show it, okay? And I will save some time for. But anyway, if you want really to talk about that, here you have specialists. You have at least three specialists, on this thing here. Okay, now let's go back to my my roadmap here, and so. As I said, so we were here for a short while, and now we are climbing up. As I said, we are in this area right now, and what's exciting here, when we are, sorry, which slide is that? Yeah. When you are in this area of 10 to the 20 and 25, etc., when you are shining the laser over a very small size, I mean spot size, like Donna said, wavelength of light, then you are producing these humongous intensities, and you are producing particles, of any kind of particles, any kind of radiations with very large energy, okay, very freely, okay. It's amazing, and so this is we call a universal source of high energy particle and radiations. And this type of course, of work is being done at Lund, not very well, in Sweden anyway. And if you are interested, there are people here. Okay, so now what we want to do now is we are producing. This was an idea from Tajima and Dawson. Toshi Tajima is a very good friend of mine, of a lot of people also. And he had this idea in 1979. He said, well, you know, looking at ducks or whatever on the lake, you know, looking at surfer and so on, he said, well, maybe we should use the same effect that is being used by surfer in order really to get particles moving. So they really wrote this very nice paper, but of course, it's 1979. So it's before 1985. So I didn't know about this effect, you know, and Toshi didn't know about the CPA, okay? So, but fortunately, we had scientists at NRL, Naval Research Lab, who really were able to saw the potential to put the two concepts, CPA and laser wake field accelerations, you know, together in order to accelerate particles. And this is what is going on now in the many, many laboratories in the world. You have lasers here, and you shine the laser on this gas jet, and you're producing a plasma, you know, which is plasma is a kind of a soup of electrons and protons and so on. And you are creating this wave, these plasma waves, where the electrons are going to be trapped and dragged at the speed of light, you know, by this wave. Okay, so this now, it is really, we were talking last night with Olga, this is really is the future for electron accelerations. And because they have a problems in high energy physics. They have a problems because they have to build these huge accelerators. Here you have the CERN accelerator, the LHC, 27 kilometers in circumference here, you know, and 170 meters underground. So it's really, of course, it costs enormous amount of money. And now, because for the next step, the next collider is going to be even bigger, okay, and will cost really an affordable amount of money. So really, it is very important really to come and with the new technology. And you think that if you're really replacing the technology used right now in this case, for instance, which is we're using radio frequency, microwave, and so on, where you have the gradients is of the order of less than 100 meters, 100 MeV per meters. That's the reason why you have 27 kilometers. But if you now are using this novel technique, the Tajima's idea to accelerate particles, then you could really fit, you know, a CERN, in principle, okay, a CERN on a football field, okay. So this is pretty good, okay. But you know, of course, we like with Toshi to look ahead all the time, and so some people, you know, in the agencies have difficulty to see that, you know, but anyway, this is the way we are, okay? And so we like to look ahead, and so right now, let me tell you that we can produce now something like devices, GeV devices are centimeter size, okay? Now we can produce up to 5 GeVs, but 5 GeVs is something like 10 centimeters in length, okay? And yes, we could really maybe put CERN on the football field, but could we do much better than that? And right now, and the reason is yes, we could, in fact, and I'm not pulling your leg here, Okay, we could really, in fact, make the accelerator kind of TeV accelerator on a fingertip, and by doing what? Okay, instead of using gas, which has a very low density of electrons, then we would like to use solid. Solid, and so you have 6 orders of magnitude larger amount of electrons, okay, because we are working also with gas at low density gas. And then, but you say, wow, but I mean, now light won't be able to propagate through the solid at this very high intensity. And so we say, okay, fine, but if we can really develop a high intensity X-ray now, so that is, instead of working in the visible, work in the X-ray regime, then the X-rays, high intensity, can penetrate into the solid and to produce this wake field. This is exactly what we are doing right now, you know, at the École Polytechnique, and in collaboration with, of course, with Toshita Jima at Irvine, and also with some people from the Eli, okay? Because we think really this is really maybe the future, trying to work with laser wake field accelerations in the high energy X-ray regime. So we have ways to do that. I don't have the time to show it, but it's really, I think there is really new avenue to do that. Now, yeah, just a quick reminder that there is this three phenomenal facilities which are being built by the European Union and which are really in Czech Republic, in Hungary, and in Romania, where you have absolutely 3 beautiful facilities were really doing different things. They don't do 3 times the same thing, of course, and and it's absolutely fabulous to have in few years, you know, we will have them working and welcoming large amount of users, and so. And Eli, for instance, is very close to get to the 10 petawatt objective. Now, you know, what is there's a big application coming back to societal applications. There's a very important applications if you can produce beams of particles. Let's suppose that you can really produce beams of protons. Well, you know, protons therapy, for example, for cancer and so on, is really the therapy of choice, okay? Because the protons, not like other radiation of particles, they don't burn the tissue between really the skin and the tumors. You can really address the tumors almost, you know, uniquely, so you can deposit your proton exactly in a tumor. Now, also, what is nice about having these high-intensity lasers is you can make particles, and these particles, you know, can be radionuclides and so on, and you can use them, you know, to implant these particles into the near the tumor or in the tumor of the patient. Also, you can use these radioisotopes and so on, but you know, which in order to do all kind of diagnostics and so on. So this CPA, high intensity or extreme light intensity or lasers, are really very useful, but will be very useful in the medical world. Now, there's also another applications, but this is dreaming. But I like to dream anyway, so I did that all my life and made my living with that. And so anyway, so there's one really big problem we have. And this also, together with Toshi, we're working on it. And by the way, we're not working because it's easy, but we're working on it because it's difficult. Okay? And what we want really to do is to transmute nuclear waste, because we have all nuclear energy is maybe the best candidate for the future, but you're still left with a lot of this junk, dangerous junk, and that's the reason Toshi invented the terms now. Toilet science. It's time to do toilet science. It's time to clean up what we have produced, producing the energy and so on for our living. And so the idea now, of course, is we have to find ways, okay, to mitigate, this nuclear waste. And one way will be maybe to transmute this nuclear waste into a new form of atoms which are not which don't have this problem of radioactivity. And so what you have to do is to change the making of the nucleus. Okay, so for example, if you have a nucleus atoms A, okay, and you have a isotope A, and which is maybe radioactive for a long time. So like take the example of technetium, for instance, and which can be radioactive for 100,000 of years. Then if you can really lodge a neutrons, because now we have freedom. We know that we can produce any kind of particles, including neutrons. We can produce neutrons, in this in the nucleus. Then you are changing the isotope A into an isotope B. But this time, it can have really now radioactivity time release of the order of seconds. Of course, this is the most favorable case. But so we would like to extend the concept, to, of course, the nuclear waste, which are really polluting our life right now. So by the way, sometimes you're lucky, and this isotope B becomes isotope C, and it's stable, so it doesn't emit anything. So, in conclusion, for me, extreme light is capable of generating the largest fields, the largest accelerations, the largest temperature, and the largest pressure. Just with light, it's amazing. And it carries the best hope and opportunity for the future of science and technology. So, thank you very much. And I would like to add that, we are doing this. It's a very rich field right now, the field of extreme light. But I think the best is yet to come. Thank you very much.
So this concludes the physics lectures for this year's Nobel Prize 2018. I would like to extend my profound thanks again to our three eminent speakers, Dr. Essiambre, Dr. Donna Strickland, and Dr. Mourou for wonderful talks. And having said that, I would finally like to invite our Nobel laureates, Donna Strickland and Gérard Mourou, to come up on stage with me so that you may congratulate them again to this year's prize. So please.